Good evening, Shalom. Welcome to yet another fascinating evening hosted by the Tel Aviv University AstroClub. To those who don't know, we are a voluntary organization of graduate students from the astrophysics department here at Tel Aviv University, and we organize many public lectures like this one tonight, and night observations, and many other activities. Unfortunately tonight, due to bad weather, we won't be able to open our telescopes, but if you're interested, you can find out more about our future events on our website and in our Facebook page. It is my great honor to introduce to you our speaker this evening, Professor Robert Kirshner, who is a professor of astronomy at Harvard University and also a close professor of science at Harvard University. Professor Kirshner graduated from Harvard and got his PhD in astronomy from Caltech back in 1975. He was a postdoc at the Kitt-Pick National Observatory and was later chairman of the astronomy department at Harvard University. He also served as president of the American Astronomical Society and is a member of the National Academy of Sciences. Professor Kirshner is the author of over 200 scientific research papers ranging in different astrophysical fields from supernovae and structure of the cosmos. He was also part of the High-Z team, which, among other things, discovered the acceleration of the expansion of the universe. He also has written a popular level book called The Extravagant Universe, which won an AAP award. And, of course, he's won many prestigious awards over the years, and he is this year's recipient of the Wolf Prize in Physics. And today, we are delighted to hear him tell us about the accelerating universe. Please, Professor Kirshner.
All right. How's that? Okay, good. Well, thank you very much. It's a tremendous pleasure to be here in Tel Aviv. I want to tell you about the accelerating universe, the history of the universe from 14 billion years ago until now. And I want to do that in 40 minutes. So to do that, I have to leave out a lot. For example, the work of others. And I will emphasize the things I've done, but let me tell you, this really is the work of a lot of people. So we know now that we're living in the Milky Way galaxy, and people knew that in 1915 when Einstein was working on general relativity. But at that time, 1915, people thought that that was the whole universe, that the distribution of stars was the universe. And this is not the story that we think of now. There's a button here. Here's the machine. That's not the way we think of it now. People learned fairly quickly in the next decade of the 20th century what our real place in the universe was. So this is an image of our Milky Way. There's no place on Earth where you can stand and see both the northern part and the southern part of the Milky Way, but you can stitch together a photograph like this one that gives the impression of our galaxy being a galaxy like the others. But this was not known in 1915. The most important thing in this picture is, I've just circled here. You'll see that there are a lot of cases where I'll have to use a circle to show you the most important thing, because it's not always the obvious thing. And that is, of course, the Andromeda galaxy. That's another galaxy, the neighbor to the Milky Way. But the understanding that these little fuzzy things, these nebulae, were actually systems equivalent to the Milky Way galaxy is something that people developed, as I said, in those first decades of the 20th century. Now, also at that time, Albert Einstein was working on the theory of general relativity, and when he applied it to the universe as a whole in 1916, he was the victim of his knowledge of astronomy, which was that the universe was the Milky Way. And his idea for what kind of solution he should have to his equations for general relativity was that the universe should be static. That is, not expanding or contracting. And the reason why it should be static, he thought, was that that's what the observations were telling us. The observations of stars in the Milky Way galaxy do not show a systematic motion away from us or toward us. They show a kind of static distribution. And so here's what he explained. If you read books about Einstein, it often says, Einstein liked the idea of a static universe because it was eternal, or something like that. That's not what he said. What he said was that term, this extra term he put into his equations, a kind of anti-gravity to balance out the gravity pulling in, that term, which we call the cosmological term, that term is necessary only for the purpose of making possible a quasi-static distribution of matter as required by the fact of the small velocities of the stars. So he doesn't say, in order to make an eternal universe, he says, to match up with the observations of stars. And here he is talking to his friend De Sitter, the astronomer who told him that Milky Way was the whole universe, but we should look into it a little further. And here they are working out equations for the dynamics of the universe. And this lambda, this factor that is the thing that he put in by hand to make a static universe, is, I think, that thing on the blackboard. Well, all right. In the 1920s, people began to understand the dimensions of our own Milky Way galaxy. By looking at stars whose brightness we knew, they were able to figure out from their apparent brightness how far away they must be. And the dimensions of the Milky Way are about 100,000 light years across. A light year is a good unit for astronomers because it tells you how far light travels in a year. And when you go out at night, on a clearer night than this one, you'll see stars that are a few light years away, or 10 light years away, or 100 light years away, or 1,000 light years away. So that's a good unit. It also is a unit that conveys the notion, a year sounds like time, the notion that light traveling to us at the speed of light takes time to get here. So in this room we have the same situation. Light travels a foot. That's a unit of distance used in the United States and I believe in Myanmar. A foot in a nanosecond, in a billionth of a second. So you never see the world the way it is. You always see the world the way it was. I see the people in the front row the way they were 10 nanoseconds ago. But curiously, the people in the back look younger because I see them as they were 60 nanoseconds ago. Just a joke in the room, but not a joke in the astronomical setting. And what astronomers found was the dimension of the Milky Way and also the interesting point that we're not at the center of the galaxy. In fact, Tel Aviv is located far from the center of the galaxy, out in a region of a spiral arm. Of course, it's not a picture of our galaxy, but of one something like it. But Tel Aviv and the Earth are located, and the Sun, oh yes, the Sun, are located in an outer region of our own Milky Way. And that's why that first picture I showed you is a kind of edge-on view where we're looking toward the center, and we see the center of the galaxy as that big bulge. Well, all right. It's humiliating, of course, not to be at the center of things, but the fact is that the history of astronomy is one in which we've been constantly demoted from Earth being at the center, and then we say, well, okay, that's not true. The Sun is at the center of the Milky Way. The Sun is at the center of the solar system. But the Sun is not at the center of the Milky Way, and as I'll show you in a second, we don't think that the Milky Way, our own galaxy, has any special role in the universe. It's more of a typical galaxy than a special one. Part of the way these measurements were made, as I said, was by looking at stars whose brightness you could measure and whose relative brightness you knew, that is, or whose absolute brightness you knew. That is, by seeing how bright something appeared, you can tell how far away it is because the apparent brightness goes down like the square of the distance, but you have to start with something that you know is the same brightness in order to do that well. And I just show you this picture of Henrietta Swan-Leavitt, who worked at the Harvard Observatory, where I work, and she was studying a certain kind of star, variable stars, Cepheid variable stars. They get bright and dim and bright again as they vibrate. And she said it's worthy of notice that the brighter variables have the longer periods. The period, the time of vibration, is something that you can measure, and that doesn't depend on how far away it is. So you can tell whether you're looking at the equivalent of a 100-watt bulb or a 50-watt bulb or a 25-watt bulb, an extra bright, medium bright, or dim star by measuring its period. And then you can measure the apparent brightness and figure out the distance with some accuracy. And that's how this map for the Milky Way was constructed. The bigger map of finding out where we are in the universe used new tools. And here's the 100-inch telescope at Mount Wilson. Now it's 2.5 meters. And it was constructed in the second decade of the 20th century, about the same time as the Titanic. And if you look at it, it has that kind of robust engineering of big plates and rivets. It has been much farther from icebergs, however, and has lasted better. Again, the most important thing in the picture is not the obvious thing. It's where the observer would be. Over there on that little chair is where the observer would be to operate the telescope, usually taking photographic plates, which was the technology for detecting light in the 1920s. And so here's the famous person who used this telescope to discover that the universe is big. This is Edwin Hubble at the business end of the 100-inch telescope, up on that little rickety platform on that little bentwood chair. And here's a photograph that he took of the Andromeda galaxy that I pointed out earlier. It's a galaxy near ours, but its distance was not known. And what he did by taking photographs repeatedly through the seasons in 1922 and 1923 was he noticed that there were some stars. He was looking originally for novae, stars that would appear, and he thought maybe he could use the brightness of the novae to estimate the distance. But then he had a star up here, which he thought was a nova. But then, when he looked at his plates more thoroughly, he realized that he had seen it before, that it was not a but a variable star. That's what this is, up here. This is, in fact, one of those Cepheid variable stars that Henrietta Leavitt had studied and that people knew about in our own galaxy. So by measuring the period, he could figure out what the intrinsic brightness was for those stars. By measuring the apparent brightness, he could figure out the distance. And the distance turned out to be not like the size of the Milky Way, but much bigger. The Milky Way has a dimension about 100,000 light years. The distances to the nearest galaxies turn out to be millions of light years. So the nearest big galaxies, like Andromeda, are millions of light years. So you're seeing light that was emitted not in historic times, but 2 million years ago when you see the Milky Way. Now, I said I was going to trace out the 14 billion year history of the universe, and I'm going to do it by talking about objects that we can see at much larger distances, where the light has been traveling to us for a very long time, half the age of the universe, that allows us to see what the universe was like back then when it was young. Okay, one more important piece, though, is something that many of you are familiar with, which is that the universe is made of kind of interchangeable bits, atoms, and the stars that we see are made of atoms which are just like the atoms on the Earth. As people began to study the properties of atoms on the Earth, they began to realize that this was a way to learn much more about the stars. Atoms on the Earth have certain wavelengths or colors where they absorb or emit light, and those same wavelengths or colors are present in the spectrum of stars like the sun. That tells us that the same chemical elements are present in the sun that we have right here on the Earth. The galaxies, those systems of stars, of course, are also made up of those same atoms. And so the idea is that you can take the light from a star, like the sun, and you can see what atoms are in it, or you can take the light from a galaxy, and it's all the mixed up light from all those many stars that you're measuring. So here's a spectrum where you take the light and you spread it out by wavelength or color. An astronomer's job is to take something beautiful, like a rainbow, and to turn it into a graph, as you see up here, where there's a kind of plot of how bright the galaxy is at each wavelength, and you can see it has these sharp dips which correspond to these dark lines in the spectrum in the spectrum. And these correspond, it turns out, to different chemical elements. So this line is due to the element sodium, this one's due to calcium, and so on. And those are wavelengths, colors at which those are detected, are very well known from laboratory studies on the Earth. But it turns out that they are generally not measured at the same wavelengths in galaxies. The first measurements of these were done by Vesto Melvin Slipher. And here he is with the spectrograph. You can see the light comes in, and then there's a set of prisms that bend the light around to a photographic plate up there. He looks like he's looking into it, but he's not. He's just kind of glowering at the photographic plate, which is a very slow thing. And by measuring the spectrum, he found that the spectra were shifted. All the lines were stretched out, usually to the longer wavelengths, occasionally crammed up to shorter wavelengths. Andromeda, in fact, is coming toward us because we know it's coming toward us because it's shifted to the blue. But most of the spectra of galaxies that he was able to measure, about 20 of them, were to the red. And this was quite a mystery in the 1920s. We're used to interpreting this effect as velocities. You know this effect from sound. The Doppler effect is the change in the pitch of an object as it comes toward you or away from you. If you stand by the side of a road and cars are coming by, you know that the pitch of the sound of the engine and the tires is higher as it's coming toward you and lower as it goes away, and you know that characteristic sound. It goes from a higher pitch to a lower pitch. If you're sitting in the car, then you don't hear any change in the pitch as you pass that poor person on the side of the road. You just hear the hum of the engine and the whine of the wheels. The reason for the fact that we hear the change, but we don't see the change when cars go by, we don't see them change color, is that the speed of sound is only 1/1,000,000th of the speed of light. So the speed of light's much higher. If the speed of light were lower, then when cars were coming toward you, they would look kind of blue, and when they were going away from you, well, they do look kind of red, but there's a different reason for that, okay? They put the filters on those taillights. Okay, so in 1925, it turns out Hubble had measured the distances to some of these nebulae using the technique I described, and Slipher had measured the velocities to galaxies. And it's a little surprising why Hubble didn't then put 2 and 2 together and make that plot that we call the Hubble diagram of the velocity versus distance. In his book, where he describes his wonderful work, he says he has a kind of physics of psychology, in which he says he had natural inertia. He said a natural inertia in the face of revolutionary ideas couched in the unfamiliar language of general relativity discouraged immediate investigation. A natural inertia. You know, if your assignment is late or if you don't do the referee's report, what is the reason for this? Well, natural inertia. Okay. Anyway, he finally got around to it. De Sitter convinced him in 1928 that he ought to plot those things against one another because he had a prediction. And Hubble did. Here's the velocity on the vertical axis and distance on the horizontal axis. And what you can see is, although the data are pretty noisy, positive on this plot means going away from us, and negative means coming toward us. Here's M31, the Andromeda Galaxy, coming toward us. Check your homeowner's insurance. And you can see that there's a relation between these two things. The nearby things are receding from us, but slowly. The more distant things, twice as far away, are receding about twice as fast. Now, Hubble's initial data was rather sparse and kind of noisy, but this effect was found to be really true. And we interpret it, although Hubble was not so sure about this, as evidence that we live in an expanding universe. Let me say a word about that. So at the institution where I'm on the faculty, and I believe that every member of the faculty, well, the tenured members of the faculty anyway, regard the universe as organized in generally this way, with them at the center. And that this observation of the galaxies only confirms the idea that they have held since childhood, that they are really special. This is one picture of what Hubble's law might mean, a universe in which every galaxy is going away from our galaxy. But a minute ago, I said, you know, we don't think we're at the center of the solar system. We don't think the sun is at the center of the Milky Way. Why would we think the Milky Way was somehow a special privileged galaxy? So you can take another point of view, which is that the universe is the same everywhere, and then it's easy enough to imagine how you would make it so the universe appeared to be moving away from you no matter where you were. And that's by just stretching out in all directions. If I had the power from Raymond and Beverly Sackler to make this room twice as big, you would find that the person who was 1 seat away was then 2. The person who was 2 seats away would be moving away from you twice as fast in the same, because they moved from 2 to 4 in the same length of time, and so on. You would see something just like Hubble's law. Now, you saw me waving my hands. That is always a sign that we are moving into dangerous territory, and it means that it's time to switch over to my other powerful means of argument, which is animation. So here's an animation in which I've taken a picture of some set of galaxies, and I've just stretched it out and stacked them up one on top of one another. And what you can see is I've just picked this galaxy, but I could have picked any other one. And the galaxy that was nearest to it has moved away. The galaxies that were more distant, like this one, have moved a bigger distance in the same length of time. It's moving away faster. And if you analyze this picture, you can measure the velocity, how far it moves, and the distance, where it was when you started, and you get Hubble's law, it turns out, if you just have something stretching out in all directions. So by waving my hands vigorously and using animation, I hope I have convinced you that that other picture is not right, that any galaxy, any viewer in the universe would see the same thing that we see, a universe that's stretching away from them. I have no idea what's on this. What about that? Well, you might wonder, what about that cosmological constant that Einstein had inserted to make a static universe? Remember, I said that there was gravity pulling in, and he put in this extra term. Right after the discovery of the expanding universe, De Sitter, the same fellow I showed you before, changed into the shape of a Greek letter lambda, and was shown blowing up this ball, which is meant to represent the whole universe. That is, the idea in this Dutch newspaper was that maybe this cosmological constant that Einstein had thought about was not such a terrible thing, that it would power or the expansion of the universe. And you can read this. This is in Dutch, but it turns out English is a dialect of Frisian, which is a Dutch language, and so you can just read this. What blows the ball up? What makes the universe expand or swell up? That has to be lambda. No other answer can be given. So that's what he said in 1930. Of course, he changed his tune. Here's Einstein at the 100-inch telescope, and he's looking in there. This is, of course, Hubble getting into the picture. Whenever they took a picture of Einstein, he wanted to be in the picture. This is the observatory director, and he looks nervous. I think he's worried that Einstein is going to break the equipment. And here's a little more formal portrait of Einstein giving a talk at the Carnegie Observatories in 1931. And there's Einstein. This is Millikan, who, of course, had worked to found Caltech. This is Hubble, tall gentleman, and he's being patted on the head by George Ellery Hale, the man who founded the Carnegie who built the 100-inch telescope, and he's patting him on the head. Good work. You've destroyed Einstein's picture of a static universe. And Einstein went quite quickly from being a little embarrassed about this cosmological constant to really not wanting to talk about it at all. So here's the statue of Einstein that's in Washington. It's outside the National Academy of Sciences. And if you look carefully at it, I climbed up on the statue at some risk of being arrested, and I took a picture of those equations, which are on that bronze tablet, which he brought down from a mountain. And what you see here are some equations. Here's one you know, E equals mc squared. Okay, everybody knows that. Here's the equation for the photoelectric effect. That's how light coming into a metal kicks out an electron, and it's related to the way we measure light now from the interaction of light with matter, producing electrons that we can measure. And up here is the equation, the fundamental equation for general relativity. It tells how the presence of matter and energy in the universe produces curvature in space. But you don't have time to go through this in great detail, but I just point out there's no lambda in that equation yet. Okay, so what about the supernovae, and what about using the supernovae to measure cosmic distances on a bigger scale? I talked about measuring distances with the Cepheid variables. It turns out that Hubble was able to do that out to distances of a few million light years. We want to measure distances to a few billion light years, a fair fraction of the age of the universe. To do that, we need something, well, we have advances in technology, so we can do better that way, but also you need something brighter. And it turns out there is something brighter. There is a phenomenon in nature, the supernova explosion, which is 1,000,000 times brighter than the Cepheid variables that Henrietta Leavitt was using. And here's an example. Here's a fuzzy thing. That's a galaxy. In the picture that Hubble was building up, the galaxies are at distances of millions of light years. And what you can see, and they contain hundreds of millions of stars. And here, for a little while, is one star. I'll show you in a second. This star gets bright and gets dim over the period of roughly a month. And once you establish the distances to the galaxies, then you know that this thing must be very, very luminous. It is about 4 billion times the luminosity of the sun. This is the kind of object we call a supernova. Supernovae, Hubble understood that the supernovae could be used to measure distances. He said supernovae can be detected at immense distances. In principle, they are a criterion of distance about as reliable as the total luminosities of the nebulae. That's what he was using at that time. But then he says, the maxima, the moment when this is as bright as it gets, are so seldom observed, and the supernovae are so rare, turns out about 1 in 100 years in a galaxy, that they contribute very little to the present problem. So the point I want to make is that a change in technology from the way we can find supernovae, has led to the supernovae becoming very, even though they are rare, becoming very powerful tools for measuring cosmic distances and probing the history of the universe, probing the history of cosmic acceleration. So here's Fritz Zwicky, who was at Caltech at the same time Hubble was at the Carnegie Observatories at Mount Wilson. And here he is with a new kind of camera that has a Schmidt camera that has a very wide field that allowed him to study many galaxies at once, to patrol them, to see whether they had a supernova. So here's again a beautiful picture of a galaxy, and this is a supernova, which is one star in that galaxy, shining as brightly as many billions of stars like the sun. And it turns out that these supernovae are a certain class of these supernovae, properly treated, I should wave my hands a lot here, are very good standard candles, very good tools for measuring distances. And the proof for that is in this little diagram. This shows velocity and distance, just as Hubble's diagram did. And you can see that the points lie along the line pretty well, better than the points that Hubble had in his diagram. The points here are all for supernovae that we measured in the relatively nearby universe. The other thing to note is that Hubble's Hubble diagram would fit in this little red square down here. So he had the phenomenon all right, but he had it just by the toenail. He and Humison, his partner at Mount Wilson, did make measurements out much farther using the 100-inch during the 1930s. But right at the beginning, he had only that little grip on things. So the idea is to use the supernovae to look at the very distant universe, light that's been traveling a long time to get here, and find out whether the expansion of the universe back then is the same as the expansion of the universe now or not. It could be that the universe is speeding up. It could be that the universe is coasting. It could be that the universe is slowing down. Most people bet that because there was gravity, that the universe would be slowing down. So you need these supernovae to do it. We know a little bit about the supernovae from our own galaxy. Here's a picture taken with an iPhone of Tycho Brahe in 1572. And up there is a new star in the constellation Cassiopeia, which was a supernova. Today, when we go to that location, we know that there was a supernova there. Here's an image that shows you optical data, radio data, and X-ray data all at the same time. So you could, no matter what, you could never see this picture. Nevertheless, it's a good one because it represents the explosion in a very vivid way. You can see that it has a pretty sharp edge. It's nearly spherical as far as we can tell. And it has all this fluffy stuff in it. This is the X-ray emission, which comes from the elements that are produced during the explosion. It turns out the energy for this kind of supernova comes from a thermonuclear explosion, where one element is transformed into another in a violent burning wave that goes through the star and that blasts it apart. And the ashes of that explosion is mostly iron. So iron is the most tightly bound nucleus. That means you can get energy out from fusion up to iron. You can also get energy out from fission down to iron. But iron is sort of the end of the road for nuclear processes. And it's the thing that you expect to make when you explode one of these stars. And you should take a personal interest in this, because you have iron in your blood. And if you ask yourself the question, where did that come from? You could say, well, it came from eating liver or something like that. But where did it really come from? It came, from the elements that formed the Earth. And then, like a 3-year-old, you could say, yes, but where did that come from? And the answer is from supernova explosions that took place before the formation of the Earth. The Earth formed about 5 billion years ago. Before that time, there was less, or 10 billion years ago, there was less of the heavy elements in the universe. And the action of stars through their nuclear fusion has been to enrich the universe in the heavy elements. So you are star stuff, just as you had suspected. You're made of the material of the universe. You're not apart from it. You're a part of it. I better stop or I'll start sounding like Neil Tyson. Okay. So when you look at this, you might say to yourself, well, if somebody might ask you, well, when was that car made? And if you're a knowledgeable car buff, you might say, and where? You might say, well, that was made in Pontiac, Michigan in 1951. But a better answer is that that car was produced by supernovae 5 billion years ago. Okay, let me show you a time-lapse image to give you a sense. This is a month's worth of data for a supernova, and you can see it gets bright and it gets dim. The energy from the radioactive elements that are produced in the explosion power the light curve. They decay away, and the supernova begins to fade with a time during which the thing is bright of just about a month. So there's this problem that Hubble understood of finding these things. They're quite rare. 1 in 100 years in a galaxy is sort of a rule of thumb number. So you could get a graduate student and assign them a galaxy, and half of them would find one in 100 years and half of them not. That's no good. Well, all right, so then you assign them 100 galaxies and say, get to it and take a look at that thing every night. And they just won't do it, is what I've discovered. They won't do it. They prefer to write computer programs and use better detectors. So let me show you a little bit about that. Here's my thesis advisor, Bev Oak. And this is a picture from about 1990, I guess. He's very happy because he's holding one of the world's largest charge-coupled devices, a silicon device for imaging. Not so different from the things that are in your iPhone. Only this is 0.24 megapixels, and it costs a lot more than your iPhone. And, you know, he's happy, but it's only the size of his thumbnail. And what's happened, of course, is that the technology for building astronomical detectors is just like, in fact, it is the technology for building computer chips. They're silicon chips. They're deposited in the same way. They're built up on the same kinds of substrates. And so here is a detector now put together as big as the old photographic plates, as big as the biggest of the old photographic plates, and it has the ability still to make astronomers very happy. As you can tell, even a guy wearing a mask, you can tell that John Tonry is very happy. So what's the point? The point is that you can image many galaxies and search many galaxies in a single night. Let's figure out the numbers. If it's 1 in 100 years, there are about 50 weeks in a year. I don't know how long vacations are in Israel, but anyway, in France, for sure, there are fewer weeks than 50. And anyway, there are about 50 weeks in a year, so that's 100 times 50 is 5,000. So if you looked at 5,000 galaxies tonight, your chances of finding a fresh supernova are not too bad. And if you look at 10 or 20 or 30,000, your chances are really very good that you'll find a supernova near the maximum of its light curve. So that's the game. Find a graduate student who can look at 30,000 of these a night, and you'll be in business. Well, of course, that's not what they do. Here is Brian Schmidt, who was my graduate student, and he's telling me how easy it's going to be to write the computer software to do the subtraction and find these things. There was another group in the field, the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley Lab, and they had 3 people working on this project for 5 years, and they had written software that could find supernovae in images of this general type. So I said, Brian, you know, these other guys have been working on this. They've got 3 people. They've been working for 5 years. I mean, how long do you think this is going to take? He said, oh, about a month. And so in about a month, he had kind of wretched software that crashed a lot, but it actually did work. And here's the basic idea, which, of course, many people have cottoned on to, of how to do it. Here's a picture. Pretend this is a picture from tonight, or yes, last night, let's say. And over here is one from a month ago. I told you it takes about a month for the supernova to come and go, so that's a good good interval if you're not interested in too much detail. And the idea is these are digital images, so you can treat them as an array of numbers in a computer, and you can subtract one from another, no problem. And when you do, all the things that were the same last month as they are this month go away. So here's a nice galaxy with this other thing down here. And when you do the subtraction, they go away. Up here, just by eye, you'd have a hard time knowing whether this thing had changed. But when you do the subtraction, taking away the way this thing looked a month ago from the way it looked last night, what you find is something new, a little dot, which might well be a supernova in that galaxy. And you can be pretty sure it's real because it has a red circle around it, and that's been the convention for this talk. It's not quite as simple as I said. In addition to measuring the distance from the apparent brightness, you have to watch out for the bad effects of dust. Even the best kept galaxy has dust in it, and some galaxies have quite a lot. The host of the supernova has some dust in it, and you don't know how much. And it only works one way. If the supernova is made to look dimmer because of the dust, you'll think it's farther away than it really is. And so you'll make a mistake in mapping out the history of the universe, mapping the velocity versus distance, because you'll think the object is farther away than it really is. So you have to have some way to deal with this. Otherwise, you can make a mistake. I at least knew that. So I got another good student. Here's Adam Rees, the day he got his PhD, and here I am. I believe that's me. I'm wearing a vest that had all the answers to the questions we asked him on it in symbolic form. So as I mentioned, there were these 2 groups, our high Z supernova team that included Brian and Adam and many others, and Saul's group based at LBL. And both teams were vigorous and discussed matters with one another. Here we are in 1997 talking about it. In 1997, Adam called me up and he said, you know, I'm having a little trouble analyzing our supernova data. So we've been measuring brightnesses and redshifts for some of these supernovae at large distances to see whether the expansion rate was the same back then as now, to see whether the universe was slowing down in the way we expected or something else. And here's Adam went to the Massachusetts Institute of Technology. That's what we call the Technion of Massachusetts. And he worked out, where he learned to put everything in a lab notebook. And so here he is. Here's his lab notebook. And if you look down here, there's this omega matter, that is, what fraction of the universe is in the form of gravitating matter for omega lambda equals 0, that is, with no cosmological constant. And the answer was minus 0.36. That didn't sound very good. Negative mass. No, that did not sound good. And I said, well, Adam, you must have made a mistake. Go find it. You forgot to divide by the square root of pi or something. And he said, no, I've done it right. I said, well, all right, get Brian to do it completely independently and, compare answers and see what the story is. By that time, Adam had moved to Berkeley. Brian had moved to the Australian National University in Australia, so that was good. We could work night and day, one person at the beginning of the day and the other. And to make a long story short, it looked like this was not a mistake. The thing that was wrong, of course, was assuming that the cosmological constant was 0. And that if you had something like the cosmological constant, something that had this springy quality to it, something that had this anti-gravity quality to it, that made the universe speed up, then you could fit the data. So here's the data. I showed you Hubble's data from 1929. Here's our data from 1998 and 99. And our points are the blue ones, few, but with small scatter. The other points from the other guys are in red. Well, maybe it's not nice to point out just how far off the graph they are. Anyway, and here are some lines that show you what you'd expect if the universe was decelerating, what you'd expect if the universe was decelerating just a little, the way we thought it might, given the amount of matter that we see in the universe. But you can see that most of the points lie above that line. And the best fit to this, even without the powerful tools of Bayesian inference that we use, you can see that these points lie above the line. That means that the supernovae are a little fainter than they would otherwise be. That means that the universe has expanded more than you would otherwise expect. So the idea is the light's traveling from the back of the room to the front of the room. It takes time to get here. During that time, the universe will expand. If it expands a little bit, the distance traveled will be small, and the supernova will appear bright. If the universe expands a lot, accelerates, speeds up, expands faster, the distance will be bigger, and the supernova will appear dimmer. So that's the sense of it. And we map this out into this diagram of how much dark energy and how much dark matter in the universe. Just to say, if you ask theorists what they expected, it would be a point over here. But these are contours that show how probable each answer is. This is our most probable one. This is our next probable one. This one, we should be willing to bet 300 to 1 that the real answer lies up here. And you can see that that's outside the contours that we had. So it was a real surprise. People thought the universe might have enough matter in it so that it was had the geometry of flat space and was just on the border between expanding forever or not. But in fact, what we see is that the universe had quite a different composition, and it was a big surprise. This is what we thought the amount of matter in the universe was from a kind of census. But the real solution was not something where the dark energy, this cosmological constant or something like it, was 0, but some kind of value up here, in which the universe had a significant component of its energy density in this weird form that makes the universe accelerate. Something very much like the cosmological constant. In fact, Einstein started to try to take credit for this. As you can see, of course he'd been dead for some time, but here he is shown on the cover of Science magazine, and if you look carefully, those of you who can read this will see that there's a lambda here on this sheaf of paper. So here's the idea. Gravitation is slowing things down. The cosmological constant, or the dark energy, which might be something like it, has this springy quality that makes the universe speed up. And there's a kind of cosmic tug of war going on between gravity, trying to slow things down, and the cosmological constant, or the dark energy, trying to speed things up. And it turns out that the cosmological constant, or the dark energy, has started to win this battle in about the last 5 billion years. Earlier than that, the density of the universe would be higher, the gravitational tug of matter would have been higher, and we think the universe was slowing down before it started to speed up. So we have this very interesting history to the universe. It's not just coasting along, it's not just slowing down due to gravity, but it's doing both things, both slowing down and speeding up. Well, what have we been doing since 1998? Of course, we've been getting more data. So here's a Hubble diagram now that shows nearby, middle distance, high distance supernovae all the way out to redshift 1. That's about halfway back to the Big Bang. And you can't see it, but I can because I'm standing in the right place. This line is curved. This line has in it a model which has a cosmological constant, or a dark energy, that's making things speed up. And this shows how well we fit at nearby and at middling distances, which is a fairly satisfactory fit to the data. If you turn to this other kind of diagram I showed before, the error, the bullseye of probability has shrunk in all dimensions, and it really doesn't intercept zero very much. So the universe really seems to have some of this accelerating stuff, this dark energy. Now you can make the measurement yourself. Here is the data all binned up, redshift and distance. So velocity and distance are things related to them. And the line that's ticking through here is for different amounts, different fraction of the universe in the form of the dark energy. And you can see that that's too small. 0 is too small. And 1, all dark energy, that's too big. But somewhere in between, and in fact, most of the way, sort of there, is about 70% of the universe is in the form of this crazy dark energy. Well, here's a guy who knows something about discovery. This is Galileo demonstrating his telescope in Venice out in front of the Doge's palace. And Galileo said, all truths are easy to understand once they are discovered. The point is to discover them. And so while you could have fit the data by eye and discovered that the universe had a large component of dark energy, you wouldn't be the first. And that seems to count. Okay, well, actually not so much. Here is another way to look at this. The gravitating stuff we know is made up of the things we can see and know about, atoms. And that turns out to be only about 4%, although I was making a big deal about it when I was talking about the iron in the Pontiac. Most of the gravitating stuff that we have in the universe is in some invisible form. We call the dark matter. It's probably not neutrons or protons. It's probably some other subatomic particle, and maybe we'll discover what it is from particle physics. And then this part, almost 3/4 of the universe, is in the form of this weird business that we just have found the evidence for just about 10 years ago, which is the dark energy. Now, when theorists show this diagram, they are very proud. They say, look, the diagram is full. And I always say, yes, but what is it full of? And in this case, it's full of our most important resource, which is ignorance. Because we don't know what the dark matter is, and we don't know what the dark energy is. So I think, you know, if you're thinking of coming into this field or you're working as a graduate student, this is very good. There is a large area where you could improve our understanding a great deal. On the other hand, I understand this is a public talk, and not everybody here is going to embark on the study of dark energy and dark matter. And so it's kind of good to think, well, how does this make you feel? You know, we're in that little tiny slice of the atoms. I'll tell you how it makes me feel. It makes me feel special. You know, Our slice of pie, for example, includes pi, which, you know, those other components can't be made into chemical compounds that are delicious like this. So beauty's in the baryons. We're in the complicated and interesting part of the world. But it is fair to ask, what is that dark energy? Is it just a name? Well, it has some properties. It has this negative pressure that makes things speed up. In the old days, Google was actually quite useful in this regard. Now, if you Google dark energy, you get these self-important websites from astronomical institutions saying how they discovered it. Okay, but if in the old days you used to get American hydroponics, they made plant food so that you could grow certain herbal products in your closet. And it says, these specialized processes are also responsible for the very distinct odor of dark energy. So it's kind of interesting that we don't know what the dark energy is, but we know it smells bad. It smells bad. American Hydroponics had a post office box in Berkeley, California, and they had another product called Supernova to help you grow controlled substances. This is not an accident. Anyway. But really, how should you think about this? Maybe in Israel this is not quite the most appropriate thing. I don't imagine you have too many snow-covered mountains. But anyway, from time to time, there must be a little snow on the Golan Heights and so on. The question is, what are you seeing here? You know, and the answer is, you think you're seeing the mountain, but of course you're not. You're seeing the snow on the mountain. And in the same way, when you look out into the universe, and you see the galaxies, you're not seeing most of the mass in the universe. You're seeing where the light is in the universe. And in the same way here, the place where the light's being reflected is from the surface of the snow. But most of the mass is the bulk of the mountain, which is invisible in this picture, but you know it's there. And in the same way, the dark matter seems to has this quality that you know it's there from the effect that it has on the visible things. You see the galaxies rotating, for example, and you can measure the amount of mass. You can look at the light bending that's produced by the mass in the universe. And most of the mass is not in the visible stuff. What about the dark energy? How do you think about that? It's not just that we made something up and it's a crazy way to talk. The fact is that we're used to this kind of argument all the time in our everyday life. If you look outside and the trees are moving back and forth, and somebody asks you, what's doing that? You say, it's the wind. You don't see the wind. You see the effects of the wind on the tree. And in the same way, you don't see the dark energy. We don't have a good way to sense the dark energy itself, but we see the effects of it on the history of cosmic expansion. Okay, enough of that metaphorical stuff. What about the future? Well, all right. I don't think the dark energy is going to be used to levitate cars, but who knows? There is a deep theoretical problem associated with the dark energy. It might be the cosmological constant, but if you poke a theorist in the arm and say, would you please estimate for me the energy of the vacuum associated with gravity, they will do it. They'll take out their fountain pen, they'll turn over an envelope shown here, and they will make a calculation that has the fourth power of something, the Planck length in it, the Planck mass, and they'll get a number that's something like 10 to the 120, where the correct answer, as measured, is 7/10. This is sort of like the personal inertia thing. You know, if you hand this in for an exam, this is not just wrong. This is incredibly wrong. This is what we call not good quantitative agreement in polite circles in academia, but other people say, that's just wrong. So there's something wrong here. There's something we don't understand about the way to treat gravity on the quantum scale. So that's not news that we don't understand quantum gravity, but it means that this is another aspect of that problem. So why is the energy associated with the vacuum so small? We don't know, but if it weren't small, the acceleration would have started very early in the universe. Galaxies would have not formed, stars would not have formed, the chemical elements would not have formed, we would not be here on the Earth. Those things are all true, but we still don't know why the energy associated with the vacuum is so small. Is it the cosmological constant, or is it something else? That's something we can measure. Because the cosmological constant makes a very definite prediction about the relation between pressure and density, and we can see whether the dark energy acts like that or not. So it turns out I'm authorized to speak on these subjects because I have a union card from the International Brotherhood of Theorists. Oh, you can't see. It's just cut off down here. It says valid to infinity. So I'm allowed to pontificate on these matters, but only a little. I did one time, and I said, you know, the universe doesn't have to make sense, but your thesis does. And then when I was at the Weizmann Institute, I saw that they had T-shirts that are made up that say that on the back. And I went there to the gift shop, and I said, hey, I'm Robert P. Kirshner. And they said, oh, that's very nice. And I said, and those are my, you know, that's my, and they said, we'll give you a very good discount. So that was nice. So here's my action for the future. I think I'm going to go back to the statue and try to put lambda possibly on the right-hand side. You have to watch out for the park police, though. They don't like it. The other thing we're doing is using the Hubble Space Telescope to measure supernovae at longer wavelengths than the optical ones that I was showing you before, out in the infrared. And this is just symbolizing this program that we have going, where we find supernovae from the ground. And so here's a ground-based picture of the kind I was talking about before. Here's a galaxy. Here's a dot, which turns out to be a supernova. When you use the Hubble Space Telescope to observe this, this is at longer wavelengths in the infrared, where the Earth's atmosphere glows brightly, and so you have a great advantage from being above the atmosphere. You get these beautiful images. Of course, you're not looking up through the wiggliness of the atmosphere either. And so we have a program using the infrared observations of supernovae to try to make this, to really determine whether it is the cosmological constant or not. So looking ahead, there will be an infrared telescope in space. The next Hubble Space Telescope successor will be the James Webb Space Telescope. It's 6.5 meters across, so that's 6.5 meters across. It has to unfold in space because it's too big for the top of any rocket. But that is supposed to get going in 2018, and that will be a very powerful tool for probing the properties of supernovae at large distances. We're building a big telescope in Chile, the Giant Magellan Telescope. It has 7 mirrors, each of which is 8 meters across, which will be used together to make a single telescope that we'll use to measure very distant and faint objects. And I just want to show you that we have this project underway. We were able to blow the top off the mountain at Las Campanas, and we're going to start construction pretty soon. So that's my story. I can't recommend a better book on the subject than this one. If you want to hear a little bit more about the story of discovering dark energy. But I did want to say one semi-serious thing about science, and that is if you go to talk to government people, as sometimes I have done, and you try to persuade them that they should fund research, the low-road arguments are the ones usually advanced. People say things like, well, you know, it's very important to have advances in technology, and they come from funding science. And that's true. And that's very important for an economy that's trying to live by its wits, like Israel or perhaps the United States. Well, somewhat the United States. Defense is very important. You want to have a technological edge. And a lot of the people in the United States Congress, I suppose in the Knesset as well, are kind of old. And so medicine is very much on their minds. And I think this is okay. I think these arguments are true about science, and no one should be embarrassed about making them. If you talk to people about making the country rich or safe or making your representatives in the Knesset immortal, well, maybe that's not such a good idea. But anyway, you know, those are arguments for science. But I don't think that's why this kind of science is important. I think that people really are curious. We really do. That's why you came here. They really want to know where we are, how we got here, and where we're going. And by trying to measure these properties of the universe, we try to answer some of those questions that are a little like the questions that 3-year-olds have, usually in an annoying tone of voice from the back of the car. So I'm just saying this this is not my vision of perfection, being rich, safe, and immortal, and bored. I think that people are curious. We want to know how the universe is constructed. We want to know how the universe works. And we should do some science just for the joy of finding out how the world works. Thank you very much.
Time for a couple of short questions from the audience.
It doesn't matter about the length of the questions. It only matters about the length of the answers. Sir.
Keep expanding. What would be the end?
Yes, yes.
The velocity goes beyond the speed of light.
Yes, yes, yes. Perhaps I should have mentioned this. So at the end I said, people want to know what the future is. And so you're asking, if you have an accelerating universe, what will be the future? That's the short form. And it's very interesting. If the dark energy is really the cosmological constant, then the expansion is literally exponential. So the bigger the universe gets, the faster it goes. I mean, exactly that. And as you said, that could mean that the expansion was faster than the speed of light. There's no rule against that. It just means, though, that instead of, as it is now, we see more and more of the universe every year. As time goes by, we would see less and less. A smaller and smaller part of the universe would be our observable universe. We would eventually be in a universe which was kind of lonely and dark, and it's just us and Andromeda, and we would have collided with each other. So the question is, how do you feel about that? Well,
Can't be jumped off.
you can't jump off. No, you can't quit. But, this isn't going to happen right away. This is, 10 or 20 billion years in the future. And, of course, not exactly testable. That is, with the telescopes, as I described, we can see into the past. So you can trust us on things about the past. But things about the future require a knowledge of what the dark energy really is. And I would say it's much too early now to say that we really could do that. If it's the cosmological constant, that's the simplest thing. That's the thing that people will tell you. If it's the simplest thing, we can predict this exponential expansion, which has this somewhat strange quality to it. But think about the end game. Suppose it was really just our galaxy plus merged with Andromeda. That would be not so different from the picture that Einstein had back in 1915 of, one big set of stars and that's it. So I don't know what conclusion to draw from that somewhat strange idea, but it does mean we really owe it to ourselves to do a good job on finding out what the dark energy is and what its properties are so that we can make a reasonable prediction of what the cosmic future will be. Okay. Yes?
There could be any correlation between, let's say, what we call the Big Bang, and then later on the epoch of the theory of inflation with Alan Guth, and then you said it was slowing down, and then now it's expanding faster and faster.
Yeah.
So maybe there is a pattern.
Right. So the question is, how does this connect to the physics of the Big Bang and possibly inflation? So the idea, of course, is that the biggest distance we can see is back to the time of the Big Bang, or the sort of fog bank of light from the hot Big Bang. But there was something before that. And one of the interesting ideas about what that was is that there was a period of exponential expansion, literally exponential expansion, the so-called inflationary era that Alan Guth and others have talked about. And there seems to be, there are good reasons to believe that might have happened. And what this is saying is that there's a second epoch starting up now of expansion that is going at an exponential rate, or might be going at an exponential rate. Whether those two things are related to one another or not, we don't know, but they certainly sound similar. They are the presence of an energy density that doesn't decrease with time is, or changes slowly, is the essence of inflation, and it's the essence of this cosmic acceleration. So maybe we shouldn't be surprised, but we were. I can tell you that. And whether these two epochs of exponential growth are related or not, we don't know, but it is an interesting thought. Is there anyone who asked a question a long time ago and it would get here pretty soon? No one in the back? Yeah, all right. Only down in the front. Okay, go ahead.
Is there currently a way to examine and understand the essence or how the behavior of the dark matter or dark energy? What is this?
Yeah. Yeah, so the question is, can't we get a better grip on the properties of the dark energy and the dark matter? For the dark matter, I think the chances are very good that we have pretty good ideas of what it might be, a subatomic particle, sort of like the neutrino, but massive. And you might find evidence for something like that at the LHC or some other, well, no, at the LHC, period. Similarly, if our own galaxy has dark matter dominating its motions, which we believe it does, then it ought to be everywhere. It ought to be in the room. And if you work out for the kinds of particles we're talking about, there ought to be about 1 particle in a liter of dark matter. And we're going around the middle of the galaxy. We're not slowly. We're going 200 kilometers a second. So that means there ought to be a wind of these things blowing through the room at 200 kilometers per second. So why don't we build a detector, is what people have thought. And we have built detectors based on the idea that it might be a certain kind of subatomic particle and that it would interact infrequently, but from time to time, with a hockey puck of germanium or a jug of liquid xenon, you know, these sort of exotic experiments. They're put underground to get away from cosmic rays and so on. Seems like a funny place to do astronomy. But anyway, you know, a mile underground. And the current situation is that the optimism of the experimenters is unbounded. They really expect that they will detect in the next few years. It's always the next generation of the detector. They will have a direct detection of the dark matter, and that would be a very interesting thing. It hasn't happened, but it could happen, I would say, any day. The dark energy is much harder to get a laboratory experiment to detect. All the measurements are astronomical measurements. None of the measurements is in a physics lab. And it's because gravity is so weak that it really is exceedingly difficult to imagine just how you would do this. It's a situation that is similar to the situation in the 1600s, when astronomers knew for sure that the speed of light was finite, that it traveled not a foot in a nanosecond, but that it would travel across the solar system in 15 minutes. Clocks were good enough so that you could tell a difference in the timing of the orbits of the moons of Jupiter when you were on the near side and when you were on the far side. And people worked out, because clocks were good enough, that the speed of light had to be, you know, maybe 15 minutes to cross the diameter of the Earth's orbit. And there was no laboratory, there was no nanosecond stopwatch available. So for ordinary distances, there was no way to make that measurement until Fizeau and then Michelson devised rather clever experiments over with spinning mirrors and so on to make that measurement. So it went for 250 years, roughly, between the time when astronomers had detected the finite speed of light and when it could be measured in the lab. I hope it won't be that long before we'll have a better measurement of the dark energy. But I wouldn't be too optimistic. The energy, the forces involved the changes involved are very, very small. I think the more promising path would be a really good theory. It's clear from this discrepancy between the simple-minded estimate for the cosmological constant and the actual value that there's something missing, and we know kind of what it is. We know it's a proper understanding of quantum gravity. We don't have that. String theory promises to incorporate gravity on the same basis as the other forces, and that sounds like a good idea, but again, it's been hard to make a really concrete prediction. So I think that's the path that will turn out to be most interesting, that somebody will have a good idea. At the moment, there are many ideas, and we don't know which of them, if any, is a good one. It's like having a weedy garden, you know, but some of those plants may turn out to be valuable. So we'll see. I think it's an important problem. I think it's 3/4 of the universe. We only discovered it 20 years ago, and we probably ought to make an effort to find out what it is. Thank you again.